Part 3, DMAIC Analyzing. In this part, with a comprehensive collection of possible factors in hand, you can use the chapters of this part to objectively eliminate the factors that aren't important and to isolate those variables that are critical. Chapter 10, Depicting and Analyzing Data Through Charts and Graphs. In this chapter, understanding the power inherent in basic charts and graphs, creating and analyzing variation and distributions through histograms or dot plots, comparing distributions with box and whisker plots, exploring variable relationships with scatter plots, and using process behavior charts to see true performance. Data is the medium in which you, a Six Sigma practitioner, work. Therefore, how you depict and analyze your data is crucial. The most important and often the most powerful tools for analyzing and communicating data are graphical. They display the nitty-gritty of what's going on in the company through pictures, charts, and graphs. These basic graphical tools, called graphs or plots, are much simpler to use than their strictly numeric counterparts, such as a table of raw data. Pictures of data often serve as a more lucrative, more intuitive way of gaining the same insights that you would from crunching numbers, and pictures make communicating your gained insight to others easy. The chief purpose of plotting and charting data is to graphically show the central tendency and the spread of variation in a measured item of interest. You can accomplish this task in a couple of different ways. Each has its advantages and disadvantages. In this chapter, we show you how to visually display your data through histograms or dot plots, box and whisker plots, scatter plots, and process behavior charts. You also figure out how to pick up on the signs and clues that the data give you when they're portrayed graphically. Using visual materials to communicate data is your best way of getting improvement team members to be integral parts of the Six Sigma breakthrough process. When team members can see the reality of performance for themselves, they're more motivated to contribute and participate in measurement and improvement efforts. Also, your visual pictures are an effective and essential prop for communicating your project details to management. Checking out dot plots and histograms. Both dot plots and histograms give you lots of information about the variation of a critical characteristic in a process. A dot plot shows the scatter and grouping of a data from a single characteristic using, no surprises here, dots. A histogram takes the data from the dot plot and replaces the dots with bars. The following sections show you how to generate these helpful graphics and understand what the graphs are telling you. Creating your own dot plots and histograms. After collecting measurements or data for a characteristic, create a dot plot for it by using the following steps. Create a horizontal line that represents the scale of the measure for the characteristic. This scale should be in whatever measure best qualifies the aspect of the characteristic you're interested in. For example, millimeters for length, pounds for weight, minutes for time, or number of defects found on an inspected part. Divide the horizontal scale of measure into equal chunks or buckets along its length. Select a bucket width that creates about 10 to 20 equal divisions between the largest and smallest observed values for the characteristic. For each observed measurement of the characteristic, locate its value along the horizontal scale and place a dot for it in its corresponding bucket. If another observed measurement falls into the same bucket, stack the second or third or fourth dot above the previous one. And 4, repeat step 3 until you've placed all the observed measurements onto the plot. To create a histogram so that you can impress your peers with a graph that has a much more complicated sounding name, replace each of the stacks of dots with a solid vertical bar of the same height as its corresponding stack of dots. Note, the vertical dimension on a dot plot or histogram is sometimes called frequency or count. Refer to the following section. Because it's pretty straightforward, the label of the vertical scale is often left off the plot, which is why we don't include it in the process here. Interpreting dot plots and histograms. A dot plot and its fancy cousin, the histogram, offer ready access to a wealth of information about the variation of a characteristic's performance. The following points are a few aspects of a dot plot or histogram to know. Plot height. The frequency. The height of dots or the bar in a dot, plot, or histogram indicates how often the corresponding value on the horizontal axis was observed. Variation's shape. The shape of the variation on a histogram comes in three basic flavors: normal, uniform, and skewed. Figure 10-1 shows a variation shape that is normally distributed, or bell-shaped. For a normal distribution, most of the observed values of the characteristic are close to a central point, with fewer and fewer values appearing as you get farther away from the central tendency. Figure 12-1's bell curve, or 10-1. Figure 10-2 shows a uniformly distributed variation for a characteristic. With uniform distribution, the variation is evenly spread out across a bounded range. That is, you're just as likely to observe a value for a characteristic at one end of the interval as you are at the other, or anywhere in between. Figure 10-3 shows a skewed distribution shape. A skewed distribution is a variation shape that isn't symmetrical. One side of the distribution extends out farther than the other side. Here is uniform and skewed. Right. Which one's uniform and skewed? This one. Okay. This one. These uniform and skewed. Yes. Don't pay attention to these yet. For like 30 seconds. Variation mode. The mode of a distribution is its most often repeated value, or in other words, its peak. Usually the variation in a characteristic has a single peak, as seen in figure 10-4. Figure 10-4. But sometimes a characteristic displays two or more modes, as shown in figure 10-5. Because two or more values dominate the variation. A histogram showing two or more distinct peaks is multimodal. Multiple major peaks aren't usual. This situation typically means that a factor affecting the characteristic's performance is causing the entire system to behave schizophrenically. When you encounter a multimodal distribution, always dig deeper to discover what factor or factors are causing the characteristic's schizophrenic behavior. Variation average. A dot plot or histogram lets you visually estimate a characteristic's mean or average value without your having to crunch any numbers. Hold your index finger up against the horizontal axis of the dot plot or histogram and move the finger back and forth across the horizontal axis until you find the point where the middle knuckle balances your distribution equally on each side. Voila! This point is the approximate average value of the variation. Variation range. The extent or width of variation present in a characteristic is immediately recognized in a dot plot or histogram. The difference between the greatest observed value, x sub max, and the smallest observed value, x sub min, creates the range of the distribution. The symbol r always represents the range, which you can calculate with the following equation, which we just said. R equals x sub max minus x sub min. Outliers. Outliers are measured observations that don't seem to fit the group of the rest of the observations, the grouping of the rest of the observations. They're either too far to the right or too far to the left of the rest of the data for you to conclude that they come from the same set of circumstances that created all the other points. When you see an outlier or outliers on a dot plot or histogram, you immediately know that something is probably different about the conditions that created those points, whether it's the process's setup or execution, or the way you measure the process. Investigate all outliers. Find out what caused their values to be so different from all the other observed values. Isolating the cause almost always leads you to discover which factors are abruptly changing the performance of the characteristic. If you want to get more quantitative with your dot plots and histograms, you can use them to calculate the proportion of observations you've measured within an interval of interest, or to predict the likelihood of observing certain values in the future. Seeing into the future is definitely powerful stuff. Suppose you measure a characteristic 50 times. Counting and adding up what's in each of the buckets on your dot plot or histogram, you observe 17 measurements that occur between the values of 5 and 6. You can conclude then that 17 out of 50, or 34% of your measurements, ended up between 5 and 6. Now, peering into the future, you can predict that if the characteristic continues to operate as it did during the time of your measurements, 34% of future observations will end up being between 5 and 6. The casinos of Las Vegas thrive in business because they use statistics this way to know what will happen when you sit down for, say, a game of craps. Comparing distributions in box and whisker plots. The problem with dot plots and histograms, see the earlier section checking out dot plots and histograms, is that they only allow you to effectively look at one characteristic's performance at a time, like putting two people back to back to see who's taller. Box and whisker plots, or just box plots, allow you to directly compare two or more variation distributions. When you need to compare value distributions from multiple characteristics, few things are quicker to make or easier to interpret than a box and whisker plot. A box and whisker plot is made up of a box, which represents the central mass of the variation, and thin lines called whiskers that extend out on either side and represent the thinning tails of the distribution. Figure 10-6 shows an example of a box plot. Making your own box and whisker plot. To create a box and whisker plot, just follow these steps and refer to figure 10-6 for a visual. All right, we got 9 steps here. 1, rank the data measurements in order from least to greatest. 2, determine the median of the data. Find the observed value in the rank ordered data where half of the data lies above and half lies below. When the number of observed points in your data set is odd, take that value in the rank, take n plus 1, or that value in the rank ordered sequence is your median. I'm just going to read through the words. You can get the book and look at the equations here on page 142 when you dig into this. For example, if n equals 99, take 99 plus 1 equals 100, and then divide that result by 2 to get 50. The 50th number in your list is the median. When n is even, the median is the average of the n over 2 and the n over 2 plus 1 values in the rank ordered sequence. If n equals 100, you'd find 100 divided by 2 and 100 divided by 2 plus 1. Those expressions give you 50 and 51. So you'd find the 50th and the 51st values and average them to find the median. Okay. Step 3. Find the first quartile, Q1. The first quartile marks the 25% point in your rank ordered sequence. 3/4 of the data are yet to come. Find the third quartile, Q3. The third quartile is the 75% point in your rank ordered sequence. 1/4 of the data is left. Find the largest observed value, x sub max, and the smallest observed value, x sub min. Draw a horizontal line representing the scale of measure for the characteristic. This scale can be in millimeters for length, pounds for weight, minutes for time, number of defects found on an inspected part, or anything else that quantifies what aspect of the characteristic you're interested in. Step 7. Mark your median and quartile values from steps 2 through 4 and construct the box. Make points for your median and quartile values. Draw a box spanning from the first quartile, Q1, to the third quartile, Q3, and draw a vertical line in the box corresponding to the median value. Step 8, add the minimum and the maximum values from step 5 and construct the whiskers. Draw 2 horizontal lines, one extending out from the Q sub 1 value to the smallest observed observation, x sub min, and another extending out from the Q3 value to the greatest observed value, x sub max. And step 9, finally, repeat steps 1 through 8 for each additional characteristic to be plotted and compared against the same horizontal scale. Figure 10-7 in the following section shows a scale with multiple box plots. When you have a large set of data for a characteristic, you may want to extend the whiskers out to only the 10th and 90th percentiles, or to the 5th and 95th percentiles, and so on, rather than to the maximum and minimum values. Then, when outlier data points fall beyond these ends of the whiskers, you can draw them as disconnected dots or stars. This method is a great way of graphically identifying and communicating the presence of outliers in your data. Making sense of box and whisker plots. Box and whisker plots are ideal for comparing two or more variation distributions, such as before and after views of a process, or characteristic or alternative ways of conducting an operation. Essentially, when you want to quickly find out whether two or more variation distributions are different or the same, you create a box plot. Figure 10-7 is an example of using box plots to compare distributions A, B, and C. In Figure 10-7, distribution B clearly has the lowest level, but it still overlaps the performance of distribution A, indicating that it may not be that different. Distribution C, on the other hand, has a much higher value and no overlap with distributions A and B. It also has a much broader spread to its variation. Other things to look for in comparative box plots include the following: differences or similarities in location of the median, differences or similarities in box widths, differences or similarities in whisker-to-whisker spread, overlap or gaps between distributions, skewed or asymmetrical variations in distributions, and the presence of outliers. Making connections with scatter plots. Dot plots, histograms, and box plots chart only one characteristic at a time. Often you need to explore the relationship between two characteristics. To do so, you use a scatter plot. Scatter plots get their name from their appearance, a scattered cluster of dots on a graph. Scatter plots are a simple yet extremely powerful tool you can use to explore and quantify the relationship between two or more characteristics. Scatter plots start to get to the root of how certain variables impact other variables, how certain inputs inhibit or enhance your ability to create your desired outcomes. This analysis is really the start of getting to the fundamental y equals f of x plus e relationship at the heart of Six Sigma improvement. Developing a scatter plot. The key to creating a scatter plot is in capturing the measurement data. To investigate the relationship between two characteristics, you need to capture measurements from the two characteristics simultaneously. If you are interested in exploring the relationship between characteristics x and y at each point of measurement, you have to collect and record values for x and y. The two characteristics you're plotting can be two inputs. One can be an input and the other can be an output. Or they can be two outputs. As long as you make your measurements simultaneously, whether they're inputs or outputs doesn't matter. With this simultaneous data collected, you are now ready to create a scatter plot. Form points from the collected data. At each of the measurement times, pair the simultaneously measured values for the two characteristics together to form an XY point that can be plotted on a two-axis graph. Create a two-axis plotting framework. Create two axes, one horizontal and the other vertical, with each being assigned to one of the two characteristics under investigation. The scale for each axis can be in millimeters for length, pounds for weight, minutes for time, number of defects found on an inspected part, or anything else that quantifies what aspect of the characteristics you are interested in. Plot each formed point on the two-axis framework. Figure 10-8 shows a sample set of simultaneous measurement data and a corresponding scatter plot. This is the table of data, and this is it plotted on the scatter plot. Scatter plots can also be created when one of the characteristic data types isn't measured on a continuous scale, but fits into discrete categories. For example, the characteristic of sales volume, measured on the continuous dollar scale, can be plotted against marketing plans 1 and 2, measured by two discrete categories. Figure 10-9 shows an example of this type of category data scatter plot. 10-9. Drawing correlations from a scatterplot. A scatterplot tells you graphically how two characteristics are related or correlated. You can then use this correlation information to explore which factors and outputs affect each other and in what way. The following sections detail the correlation factors you should be on the lookout for in a scatterplot. Assessing the amount of correlation. The amount of correlation in a scatterplot is determined by how closely or tightly the plotted points fit in a drawn line. If two characteristics aren't related, the scatter plot of the two should appear as a random cloud or scattering of points like the one in figure 10-10. Unrelated characteristics show no pattern, trend, or grouping among the plotted points, as shown here in figure 10-10. On the other hand, when two characteristics are related, a pattern, trend, shape, or grouping in the plotted points emerges in the scatterplot. When you can naturally fit a drawn line to a set of plotted points, as in figure 10-11, you know that the characteristics are correlated. For example, figure 10-11 shows the earlier scatterplot of figure 10-8 with an overall line to highlight the trend. If a line can loosely fit the plotted points, the characteristics have only a slight relationship. However, if the plotted points are tightly clustered around a line, the characteristics are highly correlated. Of course, the reason you should be concerned with how closely certain input and output characteristics are related is that you're trying to find operational leverage, which we discuss in chapters 3 and 17. You're looking for the factors or variables that can positively influence your desired performance improvement outcome as defined by your project objective statement, and the amount of correlation is a key indicator of this relationship. How closely clustered do the scatter plot's points need to be before you have evidence of significant correlation? A good rule of thumb is the fat pencil test. Imagine laying a fat pencil on top of the drawn line, fitting the plotted points. If the pencil body covers up the plotted points, it passes the test. And you can conclude that the correlation between the two characteristics is enough to call it significant. Dealing with direction of correlation. Direction of correlation comes in two types, positive and negative. Two characteristics are positively correlated if the relationship indicates that an increase in one characteristic translates into an increase in the other. Figure 10-12 shows a scatter plot with a positive correlation between two characteristics. Surveying strength of effect. Scatter plots also graphically show the strength or magnitude of the effect one characteristic has on the other. Two characteristics may be strongly correlated. See the earlier section assessing the amount of correlation. But a large change in one characteristic may still lead to only a small change in the other. Alternatively, a small change in one characteristic can be magnified as a large change in the other. The way to visualize this strength of effect between two characteristics is to look at the slope of the line fitted to the scatterplot points. Figure 10-13 shows three scatterplots, one for each of the three input characteristics' effects on an output characteristic y. The steepness of the slope of the fitted lines determines how strong an effect the input has on the output. Hint, steep slope means strong effect. As seen here in these three little examples. The slope of a line is how steep it is. The slope is quantified mathematically by comparing how much the line climbs to how much it runs across between 2 points. This comparison is formed from a ratio of rise to run. For example, given 2 points on line x sub y, x sub 1, y sub 1, and x sub 2, y sub 2, you can calculate the slope with the following equation. Rise over run equals y2 minus y1 over x2 minus x1. If the calculated slope is 0, the line is horizontal or flat. The negative slope means that the line slopes down from left to right, and a positive slope indicates that a line slopes up from left to right. As the calculated slope value gets farther away from 0, either positively or negatively, the steepness of the line increases. When you get to a slope of positive infinity or negative infinity, you have yourself a vertical, straight up and down line. In figure 10-13, you can compare the slopes of the fitted lines for each input characteristic, x sub 1, x sub 2, and x sub 3, to the output characteristic y. The scatter plot, showing a correlation with the greatest slope, indicates the greatest impact or effect on the output. So, in figure 10-13, characteristic x sub 3 has the greatest effect on the output y. In other words, you'd have to modify input characteristic x sub 3 the least to get a 1 unit change in the output y. X sub 3 is the largest point of leverage among the input characteristics. When you use a scatter plot to determine the strength of effect one characteristic has on another, the graph is often called a main effects plot. You can read a lot more about main effects plots in chapter 18. So that's what those three graphs were. Figure 10-13. Hindsight is 20/20. Observing process behavior charts. The dot plots, histogram, box plots, and scatter plots we discussed earlier in the chapter all ignore a critical element: time. None of these graphical methods takes into account the order in which the measured data are observed. Time or order can be a critical factor, especially when you're trying to figure out the causes behind variation and changes in process behavior. Under normal conditions, a process or characteristic should behave normally. This statement is more profound than it sounds. The performance of every process or characteristic has natural variation. A behavior chart graphically shows how that variation plays out over time. The following sections help you build and analyze these charts. Creating a characteristic or process behavior chart. To investigate the behavior of a characteristic or process, plot your observed measurements one at a time along an axis representing time or order, in the exact sequence the measurements occurred in real life. To create a characteristic or process behavior chart, follow these steps. 1. Create a horizontal scale representing time or order. You usually do so by creating an axis for the order in which the measurements occurred, called their run order. 2. Create a vertical axis representing the scale of measure for the characteristic. This scale can be in millimeters for length, pounds for weight, minutes for time, number of defects found on an inspected part, or anything else that quantifies what aspect of the characteristic you're interested in. Set the maximum and minimum values on this vertical scale just slightly larger and slightly lower than the maximum and minimum observed data values, respectively. That way you won't have some of your process data disappearing off the edge of your chart. Plot each observation as a dot using its order and measurement. For 3. And 4, connect the dots. Draw a line between each sequential point to emphasize the change that occurs between observations. Figure 10-14 shows an example of a behavior chart for the completion time of an assembly process. Interpreting characteristic or process behavior charts. A behavior chart not only allows you to see the normal behavior of a process or characteristic, but also lets you quickly detect non-normal behavior, variation above and beyond the expected normal level. The causes of non-normal behavior are the assignable or special causes that erode and degrade entitlement performance over the long term. More on special cause in Chapter 9. Okay. Behavior charts form the foundation of detecting and finding the root cause of non-normal behavior. Like in figure 10-14, a process or characteristic has variation that bounces around a central horizontal level on the behavior chart. Most of the observed variation clusters close to this central level. However, every now and then you see values that are further away from the center. The variation of these exceptions is completely random over time, without patterns or trends. This type of behavior is the definition of normal and is analogous to the entitlement level of variation covered in Chapter 9. The following sections present important observations for when you're looking at process and characteristic behavior charts. Variation beyond expected limits. Outliers are measurement observations that occur beyond the limits of the normal short-term variation you expect out of the process or characteristic. Observing an outlier is like rolling 5 doubles in a row with a pair of dice. 5 doubles in a row is possible, but not common. When that roll happens, you suspect that something out of the ordinary is at play, such as maybe a loaded pair of dice. In this case, loaded is just another way of saying the dice are acting non-normally. Figure 10-15 shows a behavior chart with variation outside the expected levels in those places. When you see such excessive non-normal variation, use the timescale or run order of the behavior chart as a starting point for investigating what conditions or factors are at fault. What was different at that point in time to take the characteristic or process behavior out of its normal course? The answer allows you to identify and manage the factor or factors influencing the process or characteristic performance. Typical causes of outliers include worker inattention, measurement errors, and other one-time changes to the processes or characteristics environment. For example, you may have a data outlier for purchase order processing due to an emergency in the office where 2 workers had to leave at the same time, or a purchase order in the queue for an excessive period of time because no one was around to take care of it. In Chapter 20, you'll find out much more about detecting evidence of this type of special cause variation in the performance of your process or characteristic. Trends. A trend is a steady gradual increase or decrease in the central tendency of the process or characteristic as it plays out over time. If all the conditions in the system stay constant, the level of performance of the process or characteristic also stays level. The presence of a trend in a graphical behavior plot is evidence that something out of the ordinary has happened to move the location of the process or characteristic behavior. Figure 10-16 shows a sample of a trend in the location of the variation center over time in a process behavior chart. Just like with any other evidence of non-normal behavior, when you see a trend in a behavior chart, you need to look more closely at the system to uncover what is causing the changed performance. Trends in performance are almost always caused by system factors that gradually change over time, such as temperature, tool wear, machine maintenance, rising costs, and so on. Runs. A run is a sequence of consecutive observations that are each increasingly larger or smaller than the previous observation. Figure 10-17 shows an example of 2 runs, one increasing and one decreasing within a behavior chart. Runs can be caused by faulty equipment, calibration issues, and cumulative effects, among other things. So here's figure 10-16. This one. Don't look at this. Which I mentioned like 4 minutes ago, maybe, in trends. And then here's figure 10-17, which I just mentioned. It's got the runs. And shifts. Shifts are sudden jumps, up or down, in the processes or characteristics center of variation. Something in the system changes permanently. A piece of equipment, a new operator, a change in material, a new procedure, or whatever to cause these modifications. Shifts are clearly non-normal behavior. And figure 10-18 shows an example of a process or characteristic that has experienced a shift in the center level of its variation. Big shift right there. Up next, Chapter 11, Analyzing for Value.